Good day, my name is Richard and a warm welcome to Tutoring with Richard, where we cover the South African school syllabus and nature topics. If you would like to help grow this channel, consider supporting me on PayPal, Patreon or Buy Me a Coffee. Links in the description box below. Today we're going to cover Power Machines N6. The topic of this tutorial is the reversible processes. Question 5.2. The questions included in the video. We have been asked to issue a cautionary note. When doing these questions, please use the method I'm going to show you, as this is the method that is marked correct. Using your own method to answer questions could cost you marks even though your method and answer might be right. See the cautionary notes at the beginning of the video. On a side note, watch until the end of the video. If you watch only the first 5 minutes, you will not gain a full understanding of what you need to do. There is no quick fix in Power Machines. It takes persistence, discipline and repetition. You have to use these steps in order to succeed. Let's get straight into it. Now, for this question we are dealing with a perfect gas. A reversible isothermic process of a perfect gas is shown on a TS diagram. The diagram is included in the video. The shaded area represents the heat supplied. So for our question, 0.03 meters cubed of nitrogen. The molecular mass is 28. So 0.03 meters cubed of nitrogen. Molecular mass equals 28. Contained in a cylinder behind a piston is initially at pressure 1 is 105 kPa at T1, which is 15 degrees Celsius. The gas is compressed isothermally and reversibly until the pressure 2 is 420 kPa. Now, reversing can work in both ways. You can either increase pressure and temperature or decrease pressure and temperature. In this case, we are increasing pressure and temperature. Calculate the change in entropy, the heat flow and the work done. Assume the nitrogen to act as a perfect gas. RO is equal to 8,314 kilojoules per kg. Molecular K. Now, the temperature seems to stay the same, so only the pressure changes. So now, we need to draw a diagram. Okay, this is how this works. 420, and over here, at this point, is 105. That's your pressure. Well, volume 2 is here, and volume 1 is there. Now, this is the shaded area. So as you can see how your graph goes. Now, a next graph that we need to draw goes like this. This is the shaded area. 420. And this is 105, S2, and S1. These are what your graphs should look like. This is temperature, and that is pressure. Temperature remains constant at 15, so 15 degrees. Pressure remains constant. So, looking at these two diagrams, we will use these formulas. You'll have the diagrams in a slide on the video. So just look at them carefully. So R, we need R. So that's RO over M. So the molecular is 28. And RO is 8,314 over 28. Which equals 0,297 kilojoules per kg Kelvin. So R will be important because we had to work it out. So 297 kilojoules per kg Kelvin. Next thing we do. Now we're working with a perfect gas. So our perfect gas laws apply. So our perfect gas law is PV equals mRT. So now what we're looking for is M, small m. So we have P, we have V, we have R, we have T. So it is PV over RT equals M. So what we have here is 105 times 0,03, because we have our volume, 0,297, which is R, which we got, and now we need T, times 288 Kelvin. That is 15 degrees Celsius. So we convert that to Kelvin and we get small m. Small m is equal to 0,0368 kgs. So m is equal to 0,368 kgs. 0,0. Now what we're going to do is work out the next scenario. And our next scenario states S2 minus S1 is equal to small m R ln P1 over P2. So we have P1 and P2. So S2 minus S1 equals M 0,0368 times 0,297 97, ln 105 over 420. We put this in our calculator and we get minus 0.01516 kilojoules per Kelvin. That's S2 minus S1. So what this is a decrease in entropy. So the temperature dropped. So what we need to do, and so now heat rejected, that's in the second figure. That's in the second diagram, sorry. With the second diagram, we look at T equals S1 minus S2, which equals 288 0,01516, which equals 4,37 kilojoules of energy. Now, as we have discovered when we first started this whole section, or started Power Machines N6, we learned that heat is work and work is heat. So technically speaking, if this is Q, if this is equal to Q, then by reason W equals Q. By reason. So they want the work done. The work done is 4,37 kilojoules. That is the work done. If you found this tutorial helpful, please give it a like and subscribe. It helps to grow the channel. Positive feedback is most welcome. If you would like more videos like this, consider supporting me on PayPal, Patreon, or Buy Me a Coffee. Links in the description box below. Be at peace, be kind to each other, and remember, passing well is achievable. Have a great day. Looking forward to seeing you in the next video.